Welcome to our series on AI and machine learning. In this first lesson, we'll introduce you to the fundamental concepts of artificial intelligence, or AI, and machine learning, commonly abbreviated as ML. Let's start with some definitions. Artificial intelligence, or AI, refers to the simulation of human intelligence processes by machines, especially computer systems. These processes include learning, reasoning, problem-solving, perception, and language understanding. Essentially, AI aims to create systems that can perform tasks that would normally require human intelligence. Machine learning, or ML, is a subset of AI. It involves the use of algorithms and statistical models that enable computers to perform specific tasks without using explicit instructions, relying instead on patterns and inference. In other words, machine learning is about creating systems that can learn from and make decisions based on data. Now, let's take a brief journey through the history of AI and machine learning. The 1950s marked the early beginnings of AI with the development of the Turing test by Alan Turing. The Turing test was designed to evaluate a machine's ability to exhibit intelligent behavior, equivalent to or indistinguishable from that of a human. This was a pivotal moment that set the stage for future AI research. In 1956, the Dartmouth Conference took place, which is considered the birth of AI as a field. At this conference, researchers proposed the idea that human intelligence could be so precisely described that a machine could be made to simulate it. This conference brought together some of the brightest minds of the time and laid the groundwork for the development of AI. Jumping ahead to 1997, we witnessed a significant milestone in AI history when IBM's Deep Blue, a chess-playing computer, defeated the reigning world chess champion, Garry Kasparov. This event demonstrated the advanced capabilities of AI in strategic thinking and problem-solving. In 2012, another major breakthrough occurred in the field of deep learning. A neural network called AlexNet, developed by researchers Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton, won the ImageNet competition by a significant margin. This victory showcased the potential of deep learning algorithms in image recognition and processing, sparking a renewed interest and rapid advancements in AI and ML. AI and ML are transforming numerous industries in profound ways. In healthcare, AI is being used to develop better diagnostic tools and personalized treatment plans. In finance, it helps in fraud detection, risk management, and automated trading. The transportation industry is seeing the rise of autonomous vehicles and improved logistics through AI. Entertainment has also been revolutionized by AI, with recommendation systems on platforms like Netflix and Amazon providing personalized content to users. In conclusion, AI and machine learning are not just buzzwords. They represent a revolutionary shift in how we interact with technology and solve complex problems. From its humble beginnings in the 1950s to the groundbreaking achievements of today, AI continues to shape our world in ways we could only dream of. Stay tuned for our next lesson, where we'll dive into the different types of machine learning and explore their unique characteristics and applications. Welcome back to our series on AI and machine learning. In this lesson, we'll explore the different types of machine learning and their unique characteristics. There are three primary types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Each type has distinct methods and applications, making them suitable for different kinds of problems. Let's start with supervised learning. In supervised learning, the algorithm learns from labeled data. This means that the dataset used to train the model includes input-output pairs, where the output is the label. The model makes predictions based on this labeled data and adjusts itself to improve accuracy over time. For instance, consider email spam detection. In this scenario, the algorithm is trained on a data set of emails that are labeled as either spam or not spam. By learning from these examples, the algorithm can predict whether new incoming emails are spam or not. Another example is house price prediction, where the model is trained on historical data of house features and their corresponding prices. The algorithm learns the relationship between the features and the prices, allowing it to predict the price of a new house based on its features. Next, we have unsupervised learning. Unlike supervised learning, unsupervised learning deals with unlabeled data. The algorithm tries to find hidden patterns or intrinsic structures within the data without any explicit instructions on what to look for. This type of learning is often used for clustering and association tasks. One common application of unsupervised learning is customer segmentation. In this case, the algorithm analyzes customer data, such as purchase history and behavior, to group customers with similar characteristics. These groups, or segments, can then be targeted with personalized marketing strategies. The third type of machine learning is reinforcement learning. In reinforcement learning, an agent learns to make decisions by interacting with an environment and receiving feedback in the form of rewards or penalties. This trial and error approach allows the agent to learn optimal behaviors over time. A famous example of reinforcement learning is AlphaGo, the AI developed by DeepMind that defeated the world champion in the ancient board game Go. AlphaGo learned to play Go by playing millions of games against itself, receiving rewards for winning and penalties for losing, and continuously improving its strategy. Now let's highlight the practical differences and use cases of these types of machine learning. Supervised learning is highly effective when you have a clear idea of the output you want to predict and a substantial amount of labeled data to train the model. It's widely used in applications like medical diagnosis, where the model learns from labeled examples of diseases, or in financial forecasting, where historical data is used to predict future trends. Unsupervised learning, on the other hand, is useful when you need to explore the data and uncover hidden patterns without any preconceived labels. This is particularly beneficial in exploratory data analysis, market basket analysis, or when dealing with complex datasets where manual labeling is impractical or impossible. Reinforcement learning is ideal for situations where an agent must make a sequence of decisions to achieve a goal, especially in dynamic environments. It excels in applications like game playing, where the agent learns strategies through gameplay, or in robotics, where robots learn to interact with the physical world through trial and error. In conclusion, understanding the differences between supervised, unsupervised, and reinforcement learning helps you choose the right approach for your specific problem. Each type of machine learning has its strengths and ideal use cases, making them powerful tools in the AI and ML toolkit. In our next lesson, we'll dive deeper into some key concepts in machine learning, such as algorithms, models, and the processes of training and testing. Stay tuned.
Welcome back to our series on AI and machine learning. In this lesson, we'll dive into some key concepts in machine learning, including algorithms, models, and the processes of training and testing. We'll also discuss the important topics of overfitting and underfitting. These concepts form the backbone of how machine learning works and are essential to understand as we progress. Let's start with algorithms. In machine learning, an algorithm is a set of rules or instructions given to an AI, which it uses to learn from data and make predictions. There are various types of algorithms, but two of the most fundamental ones are regression and classification. Regression algorithms are used to predict continuous values. For example, if you want to predict the price of a house based on its features like size, location, and number of bedrooms, you would use a regression algorithm. The goal here is to find the relationship between the input features and the continuous output value. On the other hand, classification algorithms are used to categorize data into discrete classes. For instance, if you're working on an email spam detection system, the algorithm would classify emails as either spam or not spam. Another example is a medical diagnosis system that classifies tumors as benign or malignant. Next, let's talk about models. In machine learning, a model is a mathematical representation of a real-world process. It's built using the algorithm, which learns from the training data and finds patterns in it. Once trained, the model can make predictions or decisions without being explicitly programmed to perform the task. The process of training and testing is crucial for building a reliable model. Training involves feeding the model a data set so that it can learn the relationships between the input features and the target outputs. Typically, we split our data into two sets, a training set and a testing set. The model is trained on the training set and then evaluated on the testing set to see how well it performs on new, unseen data. This brings us to two important concepts in machine learning: overfitting and underfitting. Both of these are related to how well a model generalizes to new data. Overfitting occurs when a model learns the training data too well, including its noise and outliers. While the model performs exceptionally on the training data, it fails to generalize to new data, resulting in poor performance. This is because the model has essentially memorized the training data rather than learning the underlying patterns. On the contrary, underfitting happens when a model is too simple to capture the underlying patterns in the data. As a result, it performs poorly on both the training data and new data. Underfitting indicates that the model has not learned enough from the data. To illustrate these concepts, imagine you are trying to teach a child to recognize animals. If the child remembers only the specific animals in the pictures you showed during training and cannot recognize new animals, that's overfitting. If the child cannot even recognize the animals in the pictures you showed during training, that's underfitting. In practice, we aim to find a balance between these two extremes. We want our models to generalize well, meaning they should perform adequately on both training data and new, unseen data. This is achieved through techniques like cross-validation, regularization, and by using more complex models or better features. In conclusion, understanding these key concepts, algorithms, models, training and testing, overfitting and underfitting, is fundamental to mastering machine learning. These concepts help us build models that can effectively learn from data and make accurate predictions. In our next lesson, we'll explore the different types of machine learning algorithms in more detail, including some advanced techniques. Stay tuned. Welcome back to our series on AI and machine learning. In this lesson, we'll explore the crucial process of data preprocessing. Properly preparing data is essential for building effective machine learning models. We'll cover data collection, data cleaning, feature selection and engineering, and normalization and scaling. Let's start with data collection. Data is the backbone of any machine learning project, and collecting it is the first step. There are various methods to gather data, including surveys, sensors, and web scraping. Surveys are often used in social sciences and market research to collect responses from people. Sensors are used in fields like environmental monitoring and healthcare to gather real-time data. Web scraping involves extracting data from websites, which can be particularly useful for gathering large data sets from the internet. Once we have collected the data, the next step is data cleaning. Real-world data is often messy and incomplete, so we need to clean it to make it usable. Data cleaning involves handling missing data, correcting errors, and removing outliers. Missing data can be addressed by either filling in the gaps with estimates or by removing incomplete records. Correcting errors involves fixing inconsistencies and inaccuracies in the data, such as misspelled words or incorrect entries. Removing outliers, which are extreme values that differ significantly from other observations, helps prevent them from skewing the model's performance. After cleaning the data, we move on to feature selection and engineering. Feature selection is the process of identifying the most relevant features or variables in your dataset that contribute to the model's predictions. This helps improve model performance and reduce complexity. Feature engineering, on the other hand, involves creating new features from existing ones to better capture the underlying patterns in the data. For example, if you have a dataset with a date column, you can create new features like the day of the week, month, or year to help the model better understand temporal patterns. Next, we have normalization and scaling. These techniques adjust the data to a common scale, which can significantly improve model performance, especially for algorithms that rely on distance measurements, such as k-nearest neighbors or support vector machines. Normalization involves transforming the data to a range between 0 and 1, while scaling adjusts the data to have a mean of 0 and a standard deviation of 1. These techniques help ensure that all features contribute equally to the model, preventing any single feature from dominating due to its scale. To summarize, data preprocessing is a critical step in the machine learning pipeline that involves several key tasks: Data collection gathers the necessary information using methods like surveys, sensors, and web scraping. Data cleaning ensures the data is accurate and complete by handling missing data, correcting errors, and removing outliers. Feature selection and engineering identify and create the most relevant features for the model. Finally, normalization and scaling adjust the data to a common scale to improve model performance. In conclusion, properly pre-processing your data can make a significant difference in the performance of your machine learning models. It ensures that the data is clean, relevant, and appropriately scaled, setting a strong foundation for building effective models. In our next lesson, we'll delve into the different types of machine learning algorithms, exploring how they work and when to use them. Stay tuned. Welcome back to our series on AI and machine learning. In this lesson, we'll dive into some popular supervised learning algorithms. These algorithms are essential tools for predicting outcomes based on input data. We'll cover linear regression, decision trees, support vector machines, SVM, and neural networks. Let's start with linear regression. Linear regression is one of the simplest and most widely used algorithms for predicting a continuous output. It works by finding the relationship between input features and the output variable. Imagine you want to predict house prices based on features like the size of the house, the number of bedrooms, and the location. Linear regression fits a straight line through the data points that best represents this relationship. The model uses this line to make predictions about new data. Linear regression is effective for problems where the relationship between variables is approximately linear. Next, we have decision trees. Decision trees are versatile algorithms used for both classification and regression tasks. They work by splitting the data into branches based on the values of the input features. Each split is chosen to maximize the separation between different classes or to predict the output as accurately as possible. For example, a decision tree might help a bank decide whether to approve a loan by splitting the data based on the applicant's income, credit score, and employment status. The tree branches out, with each node representing a decision point, and the leaves representing the final decision or prediction. Decision trees are easy to interpret and visualize, making them a popular choice for many applications. Moving on to support vector machines, or SVM. SVM is a powerful algorithm used for classification tasks. It works by finding the optimal hyperplane that separates the data into different classes. In a two-dimensional space, this hyperplane is simply a line, but in higher dimensions, it becomes a plane or a hyperplane. The goal of SVM is to find the hyperplane that maximizes the margin between the classes, ensuring the best separation. For example, SVM can be used for image recognition, where it separates images of cats from images of dogs. SVM is particularly effective in cases where the classes are well separated and works well with high-dimensional data.
Lastly, let's discuss neural networks. Neural networks are inspired by the human brain and are designed to recognize complex patterns in data. They consist of layers of interconnected nodes, called neurons, that process input data to produce an output. The basic structure includes an input layer, one or more hidden layers, and an output layer. Each neuron applies a mathematical function to the input it receives and passes the result to the next layer. Neural networks are capable of learning intricate patterns and are used in a wide range of applications, from image and speech recognition to playing games and autonomous driving. For example, a neural network can be trained to recognize handwritten digits by learning from thousands of examples. To summarize, supervised learning algorithms are fundamental to making predictions based on input data. Linear regression predicts continuous outputs using a straight-line relationship. Decision trees split data into branches to make decisions. Support vector machines find the optimal hyperplane to separate data into classes. Neural networks mimic the human brain to recognize complex patterns. In conclusion, understanding these supervised learning algorithms is crucial for tackling various machine learning problems. Each algorithm has its strengths and is suited for different types of tasks. In our next lesson, we'll explore unsupervised learning algorithms and how they can be used to discover hidden patterns in data. Stay tuned! Welcome back to our series on AI and machine learning. In this lesson, we'll explore some important unsupervised learning algorithms. These algorithms are used when we don't have labeled data and want to discover hidden patterns or structures within the data. We'll cover clustering, dimensionality reduction, association rules, and anomaly detection. Let's start with clustering. Clustering algorithms group similar data points together based on their characteristics. One of the most popular clustering algorithms is k-means clustering. Imagine you have a data set of customers with features like age, income, and spending habits, and you want to group these customers into different segments. K-means works by initializing a set number of cluster centers, then iteratively assigning each data point to the nearest cluster center and updating the cluster centers based on the assigned points. This process continues until the cluster centers stabilize. Clustering is useful in many applications, such as customer segmentation, image compression, and anomaly detection. Next, we have dimensionality reduction. Dimensionality reduction techniques are used to reduce the number of features in a dataset while retaining the most important information. Principal component analysis, or PCA, is a commonly used method. PCA works by transforming the original features into a new set of uncorrelated features called principal components, which capture the most variance in the data. This is particularly useful when dealing with high-dimensional data, where too many features can lead to overfitting and increased computational complexity. Dimensionality reduction is widely used in fields like image processing, where reducing the dimensionality of pixel data can help in efficiently analyzing and visualizing images. Moving on to association rules. Association rules are used to identify interesting relationships between variables in a dataset. Market basket analysis is a classic example of association rule mining. This technique is used by retailers to discover associations between products bought together. For example, if customers frequently buy bread and butter together, this association can be captured as a rule. If bread, then butter. These rules are helpful for making recommendations, optimizing inventory, and designing marketing strategies. The a priori algorithm is a popular method for mining association rules, which works by identifying frequent item sets and then deriving rules from these item sets. Lastly, let's discuss anomaly detection. Anomaly detection algorithms are used to identify outliers in data that do not conform to expected patterns. These outliers can indicate rare events or potential issues, such as fraud detection in financial transactions or fault detection in manufacturing processes. Anomaly detection can be performed using various methods, including statistical approaches, clustering, and neural networks. For example, in a data set of credit card transactions, anomaly detection algorithms can flag transactions that deviate significantly from a customer's usual spending patterns, helping to detect fraudulent activities. To summarize, unsupervised learning algorithms are essential for discovering hidden patterns and structures within data. Clustering groups similar data points together, helping to identify natural groupings in the data. Dimensionality reduction reduces the number of features while retaining important information, making the data more manageable. Association rules identify interesting relationships between variables, providing insights for recommendations and marketing strategies. Anomaly detection identifies outliers that do not conform to expected patterns, helping to detect rare events and potential issues. In conclusion, understanding these unsupervised learning algorithms is crucial for exploring and making sense of unlabeled data. Each algorithm has its unique strengths and applications, making them valuable tools in the data scientist's toolkit. In our next lesson, we'll delve into reinforcement learning and how it enables machines to learn through trial and error. Stay tuned! Welcome back to our series on AI and machine learning. In this lesson, we'll explore the fascinating field of reinforcement learning. This type of learning is all about agents interacting with an environment to achieve long-term goals. We'll cover key concepts, real-world applications, and a popular algorithm called Q-learning. Let's start with the definition of reinforcement learning, or RL. Reinforcement learning is a type of machine learning where an agent learns to make decisions by performing actions in an environment to maximize some notion of cumulative reward. Unlike supervised learning, where the model learns from labeled data, RL learns from the consequences of its actions, using feedback from the environment in the form of rewards or penalties. To understand RL, we need to grasp several key concepts: agents, states, actions, rewards, and policies. The agent is the learner or decision maker, like a robot or a software program. The state represents the current situation of the environment, as perceived by the agent. Actions are the choices the agent can make to interact with the environment. Rewards are the feedback signals given to the agent after it takes an action, indicating the immediate benefit of that action. Policies are the strategies or rules the agent follows to decide which action to take in each state to maximize the cumulative reward over time. Now let's discuss some real-world applications of reinforcement learning. RL is widely used in game playing, autonomous driving, and robotics. In game playing, RL algorithms have achieved superhuman performance in games like chess, Go, and video games. For instance, AlphaGo, developed by DeepMind, used RL to defeat the world champion in the game of Go. In autonomous driving, RL helps vehicles learn to navigate complex environments, make decisions in real time, and optimize routes. In robotics, RL enables robots to learn tasks through trial and error, such as picking up objects, walking, or even playing sports. One of the most popular algorithms in reinforcement learning is Q-learning. Q-learning is a model-free algorithm, meaning it doesn't require a model of the environment. Instead, it learns the value of actions and states to maximize the expected reward. The Q in Q-learning stands for the quality of an action, which is the expected utility of taking that action in a given state, following the optimal policy. Here's how Q-learning works. The agent maintains a Q table, which is a matrix where each row represents a state and each column represents an action. Initially, the Q values are set arbitrarily. The agent then interacts with the environment and updates the Q values based on the rewards received. The update rule is based on the Bellman equation, which considers the immediate reward and the maximum future reward achievable from the next state. Let's break it down with a simple example. Imagine a robot in a grid world where it needs to find the shortest path to a goal. Each cell in the grid represents a state, and the robot can move in different directions, representing actions. The robot receives a positive reward when it reaches the goal and negative rewards if it hits obstacles. By exploring the grid and updating the Q values, the robot learns the optimal path to the goal. To summarize, reinforcement learning is a powerful type of machine learning where agents learn to make decisions by interacting with an environment to achieve long-term goals. Key concepts include agents, states, actions, rewards, and policies. RL has impressive applications in game playing, autonomous driving, and robotics. Q-learning is a widely used algorithm where agents learn the value of actions and states to maximize rewards. In conclusion, reinforcement learning opens up exciting possibilities for creating intelligent systems that can learn and adapt through experience. Understanding these concepts and algorithms is crucial for anyone interested in developing advanced AI systems. In our next lesson, we'll dive into deep learning and explore how neural networks can be used for more complex tasks. Stay tuned. Welcome back to our series on AI and machine learning. In this lesson, we'll delve into deep learning, an exciting and powerful subset of machine learning that has revolutionized many fields. We'll cover the definition of deep learning, the basics of neural networks, and two specialized types of neural networks: convolutional neural networks, CNNs, and recurrent neural networks, RNNs. Let's start with the definition of deep learning. Deep learning is a class of machine learning that uses neural networks with many layers, also known as deep networks. These deep networks are capable of automatically learning features and representations from data, making them incredibly effective for complex tasks such as image recognition, natural language processing, and more. The term deep refers to the number of layers in the neural network. The deeper the network, the more layers it has. At the core of deep learning are neural networks. A neural network is composed of layers of interconnected nodes, or neurons, which are designed to mimic the way the human brain processes information. The basic structure includes an input layer, one or more hidden layers, and an output layer. Each neuron receives input, processes it using an activation function, and passes the output to the next layer. Activation functions introduce non-linearity into the network, enabling it to learn complex patterns. Common activation functions include the sigmoid function, TANH, and the rectified linear unit, ReLU. Now, let's discuss convolutional neural networks, or CNNs. CNNs are specialized neural networks designed for image processing tasks. They are particularly effective at recognizing spatial hierarchies in images, such as edges, textures, and shapes. CNNs consist of convolutional layers, pooling layers, and fully connected layers. Convolutional layers apply filters to the input image to create feature maps, highlighting important features like edges and textures. Pooling layers reduce the dimensionality of these feature maps, making the network more efficient and reducing the risk of overfitting. Finally, fully connected layers interpret the extracted features to make a final prediction, such as identifying the objects in an image. For example, a CNN might be used in a self-driving car to process images from cameras and identify pedestrians, other vehicles, and road signs. The convolutional layers detect features like the outlines of objects. The pooling layers simplify these features, and the fully connected layers classify the objects to help the car navigate safely. Next, we have recurrent neural networks, or RNNs. RNNs are specialized for sequence data, such as time series or language. Unlike traditional neural networks, RNNs have connections that loop back on themselves, allowing them to maintain a memory of previous inputs. This makes them well-suited for tasks where context and sequential information are important. Each neuron in an RNN not only receives input from the previous layer, but also from its own previous state, enabling it to process sequences of data. For example, RNNs are used in natural language processing tasks like language translation and sentiment analysis. In language translation, an RNN can read a sentence in one language, maintaining context from each word, and generate the translated sentence in another language. In sentiment analysis, an RNN can analyze the sequence of words in a sentence to determine whether the sentiment is positive, negative, or neutral. To summarize, deep learning is a powerful class of machine learning that uses neural networks with many layers to automatically learn features and representations from data. Neural networks consist of neurons, layers, and activation functions that process input data. Convolutional neural networks, CNNs, are specialized for image processing tasks, while recurrent neural networks, RNNs, are designed for sequence data, such as time series or language. In conclusion, understanding these fundamental concepts and specialized networks is crucial for leveraging the full potential of deep learning. Each type of neural network has its unique strengths and applications, making them valuable tools in the data scientist's toolkit. In our next lesson, we'll explore practical applications and case studies of machine learning in various industries. Stay tuned. Welcome back to our series on AI and machine learning. In this lesson, we'll explore the essential tools and frameworks used in the field of machine learning. We'll discuss popular tools like TensorFlow, PyTorch, and scikit-learn, provide a basic introduction to how they are used for building and training models, and offer guidance on choosing the right tool based on various factors. Let's start with TensorFlow. TensorFlow is an open-source machine learning framework developed by Google. It is widely used for a range of tasks, from training deep neural networks to deploying machine learning models in production. TensorFlow offers robust support for both deep learning and traditional machine learning algorithms. One of its key features is TensorFlow's ability to run on multiple CPUs and GPUs, making it highly scalable. TensorFlow also provides a high-level API called Keras, which simplifies the process of building and training neural networks. Next, we have PyTorch. PyTorch is an open-source machine learning library developed by Facebook's AI Research Lab. PyTorch has gained popularity for its dynamic computational graph, which allows for more flexibility and ease of use compared to TensorFlow's static graph approach. This makes PyTorch particularly well-suited for research and experimentation. PyTorch also provides seamless integration with Python, making it intuitive for Python developers. Another important tool is scikit-learn. Scikit-learn is a widely used machine learning library for Python, built on top of NumPy, SciPy, and Matplotlib. It provides simple and efficient tools for data mining and data analysis. Scikit-learn is particularly well-suited for traditional machine learning tasks, such as regression, classification, clustering, and dimensionality reduction. Its easy-to-use API and comprehensive documentation make it a great choice for beginners and for those working on smaller-scale projects. Now, let's discuss the basic usage of these tools. Building and training a model typically involves several steps: data preprocessing, model building, training, and evaluation. For instance, in TensorFlow and PyTorch, you would start by importing the necessary libraries, loading and preprocessing the data, defining the model architecture, specifying the loss function and optimizer, and then training the model using the training data. Scikit-learn follows a similar workflow, with a strong emphasis on simplicity and ease of use. Choosing the right tool for your project depends on several factors. One important consideration is the project requirements. For example, if you're working on a deep learning project that requires flexibility and dynamic computation graphs, PyTorch might be the best choice. If you need a highly scalable solution for production deployment, TensorFlow could be more suitable. For traditional machine learning tasks, scikit-learn's simplicity and efficiency make it an excellent option. To summarize, TensorFlow, PyTorch, and scikit-learn are powerful tools for machine learning, each with its unique strengths and use cases. Understanding their basic usage and knowing how to choose the right tool based on project requirements, ease of use, and community support can help you effectively build and deploy machine learning models. In conclusion, familiarizing yourself with these essential tools and frameworks is crucial for success in machine learning. Each tool offers valuable features and capabilities that can accelerate your development and research efforts. In our next lesson, we'll explore practical applications and case studies of machine learning in various industries. Stay tuned. Welcome back to our series on AI and machine learning. In our final lesson, we'll look ahead to the future of AI and delve into important ethical considerations. We'll discuss emerging trends, ethical issues, techniques to address bias and fairness, and the various career paths available in the field of AI. Let's start with the future of AI. One of the most promising trends is the application of AI in healthcare. AI is revolutionizing how we diagnose and treat diseases. For example, machine learning models can analyze medical images to detect conditions like cancer at an early stage, leading to more effective treatments. AI is also being used to personalize medicine, tailoring treatments to individual patients based on their unique genetic makeup and health data. Another exciting trend is AI ethics. As AI becomes more integrated into our daily lives, the ethical implications of its use are gaining attention. This includes ensuring that AI systems are designed and used in ways that are fair, transparent, and respect users' privacy. AI ethics also covers the development of guidelines and regulations to prevent misuse and ensure that AI benefits society as a whole. AI and creativity is another fascinating area. AI is being used to generate music, art, and even write poetry. For example, OpenAI's GPT-3 can produce human-like text, while DeepArt uses neural networks to create paintings in the style of famous artists. These creative applications of AI are pushing the boundaries of what machines can do and raising interesting questions about the nature of creativity and the role of AI in artistic expression. Next, let's address ethical considerations in AI. One major issue is data privacy. AI systems often require vast amounts of data to function effectively, raising concerns about how this data is collected, stored, and used. Ensuring that data privacy is maintained and that individuals' personal information is protected is crucial. Algorithmic bias is another significant ethical concern. Bias can occur when AI systems are trained on biased data, leading to unfair and discriminatory outcomes. For instance, an AI hiring system might favor certain demographics over others if it is trained on biased hiring data. Addressing algorithmic bias is essential to ensure that AI systems are fair and equitable. Transparency is also critical. Users need to understand how AI systems make decisions, especially in high-stakes areas like healthcare and criminal justice. Transparent AI systems that can explain their decisions help build trust and accountability. Lastly, let's explore the career paths available in the field of AI. As AI continues to grow, so do the opportunities for professionals in this area. Some key roles include data scientist. Data scientists analyze and interpret complex data to help organizations make informed decisions. They use statistical methods and machine learning techniques to uncover patterns and insights. Machine learning engineer. These engineers design, build, and deploy machine learning models. They work on developing algorithms and systems that can learn from data and make predictions or decisions. AI researcher. AI researchers focus on advancing the field of AI by developing new theories, algorithms, and technologies. They often work in academic institutions, research labs, or tech companies. AI ethicist. AI ethicists examine the ethical implications of AI and work on developing guidelines and policies to ensure that AI is used responsibly. They address issues like bias, privacy, and transparency. In conclusion, the future of AI holds tremendous potential, with transformative trends in healthcare, creativity, and ethical considerations. Addressing ethical issues such as data privacy, algorithmic bias, and transparency is crucial to ensure that AI benefits all of society. Understanding techniques to identify and mitigate bias can help create fairer AI systems. Finally, the growing field of AI offers diverse career paths, providing exciting opportunities for those interested in shaping the future of technology. Thank you for joining us on this journey through AI and machine learning. We hope you've gained valuable insights and are inspired to explore this dynamic and impactful field further. Stay curious and keep learning.